Have you ever wondered how the most powerful and feared weapon on the planet is made? Behind a nuclear bomb, a device capable of destroying an entire city in a matter of seconds, lies a process. From the extraction of uranium in underground mines to its integration into intercontinental missiles or strategic bombers, how science, engineering and military technology combine to shape the greatest destructive force created by humankind. Today, humanity coexists with one of its most feared creations, nuclear weapons. It is estimated that there are more than 13,000 operational nuclear warheads on the planet, distributed across different countries that consider them the ultimate military deterrent. These devices are so powerful that in just seconds they could wipe out a densely populated city or even render an entire region uninhabitable for generations. Since their invention, these bombs have been hailed as the ultimate expression of human destructive power. Their very existence has shaped international politics for more than 7 decades. However, behind all their symbolism lies a question many are asking: how is a weapon of such power built? It all begins deep within the Earth, in deposits hundreds of meters below the surface. There lurks uraninite, a dark mineral that at first glance might pass for ordinary rock. But inside it harbors a component that changed history, uranium-235. The great challenge lies in the fact that this isotope is extremely rare. Less than 1% of the total material is actually useful for energy or military purposes. To obtain just 1 kilogram of enriched uranium, approximately 500 tons of rock must be processed. Imagine the magnitude of the operation. Entire mountains removed to obtain just a few key pieces. Uranium mines are veritable underground cities. Giant excavators, hydraulic drills and heavy-duty trucks work tirelessly. Each block of rock is extracted under rigorous safety measures because although the mineral is not immediately fatal in its solid state, constant exposure to radiation can cause serious health problems for workers and even contaminate the environment. Once the rock is extracted, tons of this material are transported in armored vehicles to processing plants. And that's where the true transformation of the mineral into an element capable of unleashing one of the most powerful forces in the universe begins. When the uranium arrives at the plant, the first step is cleaning and preparation. It is unloaded into huge steel hoppers and moved along conveyor belts to pre-treatment areas. High-pressure water jets and vibrating machines remove traces of mud, dust and other surface impurities. What remains is uranium-laden rock ready to be crushed. In giant crushers, the material is reduced to a fine, dark powder. This powder is then immersed in highly acidic chemical solutions. The goal is to dissolve the remaining minerals and isolate the most valuable component, uranium. The product that emerges from this process is a yellowish substance, known in the nuclear industry as yellow cake. This paste is toxic and radioactive, but it's still far from being useful in a weapon. To achieve this, it must move on to the next crucial step, enrichment. The yellow cake is transformed into uranium hexafluoride UF6 gas, which is then introduced into enormous industrial centrifuges. These machines spin at dizzying speeds, and thanks to centrifugal force, are able to separate the different uranium isotopes. The only one of interest is uranium-235, as it is the only one capable of generating a nuclear chain reaction. The result is a metallic grey powder, much more concentrated and extremely dangerous. Even in small quantities, if not handled properly, it could have fatal consequences. This material is stored under maximum security protocols before moving on to the most delicate phase, the manufacture of the explosive core. Enriched uranium becomes the heart of the bomb, the fissile core. It's the component where the chain reaction that releases nuclear energy occurs. To understand its power, one example suffices. A golf ball-sized fragment can release as much energy as 20,000 tons of TNT. Therefore, handling this material requires an almost surgical level of precision and care. In highly restricted laboratories, specialized technicians melt and mold the enriched uranium into spherical or cylindrical shapes. Ultra-precision machining machines then fine-tune every surface. A tiny imperfection could cause the bomb to malfunction, or worse, accidentally explode. The goal is to gather the exact amount of uranium required to reach what is known as critical mass, the point at which a self-sustaining nuclear chain reaction begins. Once ready, the piece is encapsulated in special materials designed to withstand heat, pressure and radiation. At first glance, it looks like any ordinary block of metal, but in reality, it's the most dangerous piece of metal ever created by humans. A uranium nucleus doesn't explode on its own. For a nuclear reaction to occur, it must be compressed with absolute precision. This is where the detonation system comes into play. Around the core, military engineers place up to 30 high explosive charges, similar in power to C4 explosive. These charges are designed to detonate simultaneously, generating a uniform shockwave that compresses the uranium from all angles simultaneously. The design is so complex that any timing error could render the bomb useless or cause it to detonate prematurely. To prevent this, altitude sensors, electric detonators, timers, and multiple redundant safety systems are installed. Once assembled, the pump is enclosed in a reinforced metal casing that can be over 4 meters long and weigh more than a ton. This casing protects the device during transport and keeps it stable until ready for use. Once the nuclear bomb has been assembled into its final structure, a crucial phase begins: verification and assurance of its operation under extreme conditions. This stage is essential to ensure the device can withstand any real-world transport or deployment scenario without compromising its integrity. Initially, the bomb does not yet contain an active fissionable core. This allows for a series of rigorous tests without the risk of detonation. The prototype undergoes constant vibration tests, designed to simulate the shocks it might experience during a bomber flight or when loaded onto a military transport vehicle. Sudden acceleration tests are also carried out, replicating the impact of a launch from an intercontinental ballistic missile, where the force exerted by velocity can reach extreme levels. Another critical test involves exposing the device to drastic temperature and pressure variations, recreating what it would face when passing through different layers of the atmosphere or being stored for long periods underground. Each of these tests seeks to confirm that the internal systems, from the protective casing to the detonation circuits, will maintain their reliability under any circumstances. Once all the tests are passed, the genuine fissionable core is inserted and secured within a specialized armored container. From that moment on, the bomb is considered fully operational. It is transported to its final location in military convoys, escorted by armed ground and air forces, minimizing any possibility of accident or external attack during transit. A nuclear bomb is not produced to remain indefinitely stored in a warehouse. Its design is conceived so that, once the construction and testing phases are complete, it can be incorporated into strategic platforms that guarantee its immediate use. Integration into delivery systems is, therefore, one of the most delicate and decisive stages. Depending on the military strategy and the type of target, these weapons can be deployed on various deployment vehicles. Some are mounted on strategic bomber aircraft, such as the B-2 Spirit or the B-52, capable of flying long distances, penetrating air defenses, and delivering their payloads with studied precision. Others are installed on nuclear submarines, which have the ability to remain submerged for months and move stealthily anywhere in the world, ensuring a hidden and difficult-to-detect retaliatory power. However, the most feared, due to their range and speed, are those integrated into intercontinental ballistic missiles, ICBMs. These projectiles, once launched, can travel across entire continents in less than 30 minutes, carrying a payload capable of transforming the outcome of a war in a matter of moments. The loading and assembly operation on these platforms is not simple. It is carried out using highly controlled systems that include hydraulic cranes, automated platforms, and reinforced anchoring mechanisms, all supervised by teams of specialized technicians working under maximum safety protocols. Every movement must be executed with absolute precision, as the slightest error could compromise the stability of the weapon. The use of a nuclear weapon is not a decision to be taken lightly. Activation requires extremely strict protocols and direct authorization from a country's highest authorities. Once the order is confirmed, a precise and timed procedure begins that activates the delivery system. In the case of an intercontinental ballistic missile, it can be launched from fortified underground silos or from strategic submarines hidden deep in the ocean. Once airborne, it reaches speeds of around 25,000 kilometers per hour, traveling vast distances in a matter of minutes. In the case of strategic bombers, the bomb is released from high altitude and descends toward the target, guided by military GPS systems and sensors calibrated with pinpoint precision to ensure it hits the exact spot. The most critical moment comes just before the collision. At that moment, the complex detonation system is activated. The conventional explosives arranged around the fissile nucleus ignite simultaneously, generating a uniform pressure that compresses the enriched uranium beyond the critical mass. That fraction of a second triggers a self-sustaining chain reaction. What follows is an unprecedented release of energy. A glowing sphere hotter than the core of the sun instantly forms, generating a shock wave that devastates everything within several kilometers. The released radiation contaminates the surrounding environment, leaving lasting effects for decades. The power unleashed is so colossal that a single bomb has the capacity to completely destroy a modern city. And in a scenario where several are detonated simultaneously, the consequences could wipe out an entire country in a matter of minutes. In the entire history of humanity, only 2 nuclear bombs have been detonated in a real conflict. Those dropped by the United States on the Japanese cities of Hiroshima and Nagasaki in August 1945. That event not only precipitated the end of World War II, it also opened a completely new era in history, the atomic age. For the first time, humanity realized it had reached a level of destructive power capable of threatening its very survival. The images of cities reduced to ashes, the instant casualties, and the effects of radiation marked a before and after in the global consciousness. Since then, nuclear development has not stopped. During the Cold War, the United States and the Soviet Union accumulated thousands of warheads in a power play, where the threat of mutually assured destruction was a reality. Destruction was the main deterrent. Decades later, although arsenals have been reduced, more than 13,000 nuclear warheads remain active around the world, distributed among several powers. The debate persists. For some experts and political leaders, these weapons act as a necessary evil, a guarantee that no country will dare to start an all-out war for fear of a devastating nuclear response. For others, their very existence is a latent threat that should never have been allowed, as an accident, a miscalculation, or an unforeseen escalation could trigger a global catastrophe. In this fragile balance, humanity continues to live under the shadow of the most destructive weapons it has ever created.